learning Jordan's lemma, solving the integral using this lemma. First, I have to introduce this Jordan's inequality, which states that sine of theta lying between 2 theta over pi and theta for theta lying between 0 to pi by 2. Now, if you look at the graph, this orange colored line, this is for y equal to 2 theta over pi. This green color is for y is equal to theta, this one. And this pink colored, you all know this is for y equal to sine of theta, right? So this is the Jordan's inequality. And then is the Jordan's lemma, which states that if fz is tending to 0 uniformly as z tends to infinity and fz is meromorphic in the upper half plane. Now what is a meromorphic function? A function which is having only poles as the singularities, right? Then this Jordan's lemma, this states that limit r tends to infinity on integral over this tau, which is your semicircle in the upper half plane, e the power iota mz fz dz is equal to 0. So this integral is 0 provided that fz must tends to 0 as z tends to infinity, and it should be a meromorphic function, right? Next. Now, on what kind of integrals we can use this lemma? So integrals of the kind negative infinity to positive infinity are the limits, and px over qx, where px and qx are the polynomials, and then I'm having sine of mx dx, right? So integrals having sine of mx or cos of mx, and px over qx as the ratio of the polynomials or fraction of the polynomials. In such kind of integrals, I have to use this Jordan's lemma, right? How to use, I will explain you. Now this px and qx are polynomials such that degree of px should be less than degree of qx. Second, if you take qx equal to 0, then it has no real roots, right? And then we have to integrate always fz is equal to pz over qz e the power iota mz. This you have to remember, that I have to always integrate fz equal to this pz over qz e the power iota mz. From here I have to start. Then your C is the contour, that original one, along the real axis from negative r to positive r, followed by this tau semicircle from positive r to negative r. And r is large enough to include all the poles of the integrand in the upper half plane, right? So we must check which poles lie inside this contour. Alright, steps are very much, all the steps are same. Integral over c fz dz is equal to integral minus r to positive r fx dx, because when we integrate along the real axis I have to use x. Then along the tau I will use the variable z. This is equal to 2 pi iota times sum of the residues. This is your Cauchy residue theorem. And then put the value of fx over here, which is, yes, px over qx e the power iota mx. So then the second integral and this. Now according to Jordan's lemma, because fz is meromorphic function and also tending to 0 as z tends to infinity, so for that this integral will be 0 according to Jordan's lemma, and we will lefting up with this only. Just put e the power iota mx as cos of mx plus iota sine of mx. If you need your result in cos of mx, then you have to equate in real parts. And if you need your result in sine of mx, then you have to equate this imaginary parts, and then you will get the result. Let's start with the example. Prove that integral 0 to infinity cos of mx over x square plus a square dx is equal to pi over 2a e the power negative ma, where m and a are strictly positive. Then I have to deduce that from this result, that integral from 0 to infinity x sine mx over x square plus a square dx is equal to pi over 2a e the power negative ma. So let's start. Now we will integrate fz. Now what is my fz? Yes, what is my fz? Very good. It is e the power iota mz over, instead of x square plus a square, I will use z square plus a square. I have to integrate this fz. Okay, do write e the power iota mz instead of cos of mx along this contour C. Now the poles. Clearly fz has poles at, yes, take this denominator equal to 0, then z is equal to plus minus a iota. Now which pole lie inside this contour? Positive a iota or negative a iota? Of course, plus a iota lies inside this contour. Now calculating the residue for this, I am using the short trick method because I am not having any powers in the denominator. What is my function? Fz is e the power I times z over z square plus a square. Just put the value of z at the numerator because the pole is a iota. So I have to write in the numerator in place of z e the power iota m, this is a iota, over, take the derivative in the denominator. What is the derivative of this denominator with respect to z? It is 2z. Put the value of z over here now. 2 into this a iota in place of z. Very fine. So this comes out to be e the power negative ma, because iota square is minus 1 over 2a iota. Now apply the Cauchy residue theorem. We get integral over c fz dz equal to 2 pi iota times the sum of the residues. Because I am having only one residue for one pole, so only I have to write this, the value of first residue. And then this contour is splitting up into two. Now this along the real axis and then along the contour, this semicircle tau. So this is equal to, now iota cancel, 2 and 2 is also cancelled. So this is pi over a e the power negative ma, and marking this as 1, let's say. Okay, instead of fx dx, I'm writing here e the power iota mx, yes, x square plus a square. And then for this tau, I have to write e the power iota mz over z square plus a square. And this is pi over a e the power negative ma. Already I have marked one, so I'm just erasing this. Now since 1 over z square plus a square, this is meromorphic, yes. So this is tending to 0 uniformly as z tends to infinity, of course. This is tending to 0 and this is meromorphic in the upper half plane. Only singularities are poles, right? So by Jordan's lemma, this integral is 0. So integral over tau e the power iota mz over z square plus a square dz. Now when this will be equal to 0, if I put the limit, r tends to infinity, so this is equal to 0. Now here I have to let in 1 r tends to infinity. When I let r tends to infinity, then only I can take this integral as 0. So I have to write, letting r tends to infinity in 1, we get negative infinity to positive. This is e the power iota mx over x square plus a square. This is 0. This is equal to dx. Pi over a e the power negative ma. And now minus infinity to infinity. Next step is e the power iota mx can be written as cos of mx plus iota sine of mx over x square plus a square dx is equal to pi over a e the power negative ma. Now on the right hand side, I'm having the real part. So I have to equate the real parts as I need cos of mx as a required result. So just equating the real parts. So this is negative infinity to positive cos of mx over x square plus a square dx is equal to pi over a e the power minus ma. Now because cos of mx over x square plus a square, this is even function. So this integral will be 0 to infinity twice cos of mx over x square plus a square dx is equal to pi over a e the power negative ma. And finally, I have got my result. Cos of mx over x square plus a square dx is equal to pi over 2a e the power negative ma. Marking this as 2. Now final part is the deduction, right? Now I need sine of mx into x, right? If you just see, that is nothing but if you differentiate this 2 with respect to m, then you will get the deduction result also, right? So just differentiating 2 with respect to m. So I will get 0 to infinity. Yes, cos of mx is negative. The differentiation is negative sine of mx. And then the integral with respect to m, this is x square plus a square as it is, dx is equal to pi over 2a, yes, e the power minus a, differentiation is same, and then this minus a. So this is pi over 2a e the power negative ma with negative sign. And here a is cancelled out with this a. 0 to infinity negative x sine of mx over x square plus a square dx. This negative sign cancelled out with this, and we will get the result x sine of mx over x square plus a square dx is equal to pi over 2 e the power minus ma. Yes, hence ends up the result. Thank you so much for watching this video. Do like and subscribe for the latest videos. Thank you so much. Thank you. God bless you. Goodbye.